Hello, my name is Jo Won and I'm working in master's course at Hanyang University in Korea. So if you have a question to me, please contact to this email. Today's topic is theoretical behind of silicon germanium, which is used in channel materials. Let's start. From 1970 to early 2000, semiconductor scale was downsized to enhance the performance. It is quite simple to shrink the size. But in early 2000, the problem was occurred. When we reached to 90 nanometer node scale, the gate oxide thickness is about 1.2 nanometers. So downsizing the scale is limited. But luckily, despite the limiting oxide scale, the expected enhancement in transistor performance was obtained by Intel by introducing strain engineering for enhanced channel mobility. In this technology, silicon germanium source drain regions were selectively grown on pipettes for enhanced hole mobility, while silicon nitride was deposited on NFETs for enhanced electron mobility. For this technology, performance was enhanced while the oxide thickness was almost constant until we reached to 65 nanometer node scale. This can be the three main innovations under 100 nanometers. The three main innovations were channel strain engineering, high-K metal gauge technology, tri-gauge device architecture. But in this video, I will tell you about channel strain engineering only. The drive currents of the transistor can be explained in this way, where Q is the carrier charge and V is the carrier velocity. Q is given by carrier, so carrier velocity V could be decide drive performance. In terms of effective mass, reducing carrier effective mass can increase the carrier velocity. So people want to use another material which is lighter than silicon like germanium. In figure 1.12, it shows a semiconductor group and 3-5 materials and the bubble size defects, the relative transport effective mass, solid for electrons, dashed for hole. As you see, germanium has the lowest hole effective mass in here, so we can operate a lower voltage. Band gap is also concerned, so in this picture A, graph shows the band gap according to germanium fraction. As germanium fraction is high, band gap decreases. And I will tell you a reason simply. This is the lattice constant of the silicon and germanium. The lattice constants of the silicon germanium would be a middle of the silicon and germanium. So in this case, there is a tensile strain to silicon and compressed strain to silicon germanium. I will show a picture. This is the picture of the tensile strained silicon and compressive strained silicon germanium. Both of the compressive and tensile strain split the conduction band to 4 and 2 bellies, and also split the balance band to heavy hole band and light hole band like this. So it affects the lowering band gap compared to normal. Because of this case, you can see the better performance using silicon germanium. In 1.13, there is a graph of hole mobility of silicon and germanium. After material gets strained, their mobility increases. And in 1.14, there is a graph of delay according to drain voltage. You can see that silicon germanium is more faster than silicon for P MOSFET channel. So effective mass and band gap by strain of silicon germanium can enhance the performance. This is the end of my video. Thank you for listening. Bye.